Welcome to the Deep Dive. We are your shortcut to being genuinely well-informed. We take that stack of source material you share with us, we cut through the jargon, and really extract the specific high-value insights. The goal is simple: help you understand a complex topic quickly and thoroughly. So I want you to just picture this for a second. Fast forward maybe 50 years. What will the 21st century really be remembered for building? We often think of construction as, muscle, mud, maybe manual labor, like a process that hasn't fundamentally changed since, the invention of the crane.
Right.
But that picture, it's really quite outdated now. The global building industry is undergoing this massive digital overhaul. It's moving drastically beyond just pouring concrete.
Oh, it's much more than an overhaul. I'd agree with that. It's really a revolution built on data. Our source materials today, they give us this deep, really fascinating snapshot of this technological transformation. And the industry itself is starting to call it smart construction. Smart construction. Okay, so our mission in this deep dive is to guide you through this shift. It sounds pretty complex. We're going to define, the core concept. What is smart construction? We'll identify the cutting-edge digital tools driving this change. We want to get into the mechanics, right, how they actually work. And then, crucially, we'll look at the immediate quantifiable benefits, things like efficiency gains, safety improvements, which are vital. And then maybe peek ahead at the wild frontier of AI and 3D printing.
Right. And starting with that core idea, smart construction is essentially the strategic marriage of two fields that historically were pretty separate. You've got your traditional rigorous engineering principles on one side, and on the other, these advanced digital tools. It's really a shift from, let's say, analog guesswork and old paper plans to data-driven precision. And the result is systems that are fundamentally faster, safer, and just infinitely more predictable. Okay, that fusion engineering meets digital intelligence. That's the foundation.
Yeah.
So let's unpack that a bit. If we look at this new digital toolbox, what specific technologies are actually taking all this site data, which, like you said, used to be trapped on blueprints, and turning it into these real-time streams that a whole global team could potentially access?
Yeah, this is really where you see the immediate practical changes happening on, pretty much every modern construction site. Our sources consistently highlight that the success here really hinges on the synergy between three foundational technologies. These basically govern planning, collection, and verification. And the idea is to move data seamlessly, from the ground up to the digital model and then back again.
Right, creating that loop. And I gather the sort of undisputed king of that digital ecosystem is building information modeling. B.I.M, it keeps coming up in the sources as a central nervous system, the core planning tool.
Absolutely. B.I.M is, it's way more than just a 3D model, though that's how people often think of it. It's actually an intelligent database. Think about it. Traditionally, designs were 2D CAD, maybe 3D CAD, but they created blueprints that were essentially static instructions, like a picture. B.I.M, on the other hand, attaches critical data to every single element in the model.
Like what kind of data?
Oh, everything. The structural properties of a specific steel beam, the R value or cost of a window, the required curing time for a particular concrete mix. It's all embedded. So when you implement smart construction, all the data collected by the other tools we'll talk about, drones, sensors, it all feeds into this central B.I.M model.
Okay, so it's dynamic. It updates.
Exactly. And what really elevates B.I.M from just a planning tool to a deep analytical tool is its capacity for what's called 4D and 5D modeling.
4D and 5D. Okay, break that down.
Right. So the 3D model gives you the spatial data, the physical dimensions. The fourth dimension, 4D, integrates time and scheduling data. This lets project managers run simulations of the construction sequence. They can actually see potential bottlenecks, clashes in scheduling long before they happen on site.
So it's like a digital rehearsal of the whole construction process.
Precisely.
That must save a fortune in delays right there.
It does. And then you add the fifth dimension, 5D, which integrates cost data. So as you virtually build the structure in the B.I.M software, it provides instantaneous cost estimates and quantity takeoffs.
Instantly.
Yeah. So say an engineer modifies the design slightly, maybe uses a bit less steel in a certain area. The 5D model immediately updates the material cost and the total project budget. This capability, especially something called clash detection.
Clash detection.
Yeah, it automatically flags where things conflict in the design. Like if a plumbing pipe is designed to run straight through a main structural beam, obvious problem.
Right.
Here.
You'd want to catch that before you build it.
Exactly. Catching those errors in the digital design phase, not when crews are on the job site trying to figure it out, that saves monumental amounts of time and money. Fixing it later is incredibly expensive.
Okay, so BIM is the master plan, the brain constantly optimizing the design. But like any brain, it needs sensory input, right? It
Yeah.
needs to know what's actually happening on the ground to see if reality matches the plan. And that's where the eyes in the sky come in. The sources really emphasize drones for site surveying, rapid, repeated surveying.
Yes, drones or UAVs, unmanned aerial vehicles, they've become the primary data collectors on a smart construction site. They effectively replace the need for that slow, traditional ground surveying, the method involving highly skilled human teams using tools like total stations or theodolites.
Yeah, I've seen those guys with the tripods. Looks painstaking.
It is. And it often took weeks to accurately map a large construction area. Plus, you could only really afford to do it periodically, maybe at major project milestones. Now, with drones equipped with high-res cameras or sometimes LiDAR scanners.
LiDAR, like in self-driving cars.
Similar principle, yeah. Light detection and ranging. It uses laser pulses to measure distances and create incredibly detailed 3D maps. So, a drone flight might only take 15 to 20 minutes, even for a large site. During that flight, it captures thousands, sometimes millions, of data points using a process called photogrammetry.
Photogrammetry.
It basically involves taking lots of overlapping aerial images from different angles. Software then stitches these images together to create a massive, highly accurate 3D representation of the site. It's called a point cloud.
A point cloud. Got it. So that transition, you're saying from weeks of surveying down to maybe 20 minutes,
Yeah.
and from just occasional checks to potentially daily high-res data,
Mm-hmm.
that's a huge shift in visibility for a project manager.
It's absolutely phenomenal. The critical difference is both the accuracy and the frequency. Site managers can take that drone-generated point cloud, that 3D map of the current site conditions, and overlay it directly onto the 3D BIM model, almost instantly.
So they can compare plan versus reality side by side.
Exactly. They can verify precisely what was built yesterday against the plan, confirm elevations are correct, verify that the right amount of earthwork was moved, ensure material quantities on site match the schedule. This continuous verification cycle just accelerates decision-making dramatically, and it significantly reduces material waste and costly errors that happen when people are working from physical measurements that might be even slightly outdated.
Okay, so we've got BIM for planning, drones for verifying the site matches the plan. But what about the actual materials, like ensuring the quality of the concrete itself? There's a fascinating piece in the sources about technology that actually touches the building materials real-time sensors. Where are these being used and what critical function are they serving that we couldn't really do properly before?
Right. This moves us into ensuring quality assurance almost at a molecular level, specifically within the curing process of concrete. Concrete, as you know, is the backbone of most large structures. Its strength is critical. The sources focus heavily on sensors that are embedded directly into the concrete mix at the time of the pour. Tiny little sensors.
Embedded right in the wet concrete. Wow. Because historically, right, you pour concrete and then you basically wait. For days, maybe weeks, you take these physical core samples, like little cylinders of concrete, send them off to a lab, and you essentially cross your fingers and probably add extra buffer time to your schedule just to be safe, waiting for those results.
That's exactly right. And that waiting period, waiting for lab results on those test cylinders, is one of the biggest drivers of the overall construction schedule, and very often a source of major delays. You simply cannot start the next phase of construction, whether that's building the floor above, loading that concrete slab, or stripping off the expensive wooden or metal formwork that holds it in place while it cures. You can't do any of that until you have confirmation that the concrete has reached a specific, guaranteed compressive strength. The old method relied on very conservative time estimates and, importantly, destructive testing. You had to break those cylinders, and it was always delayed information.
Okay, so how do these embedded sensors change that?
They completely eliminate that bottleneck. These new sensors utilize what's called the maturity method.
The maturity method.
Yes. They continuously monitor the concrete's internal temperature history from the moment it's poured, because the chemical reaction that causes concrete to gain strength, it's called hydration, is directly related to both temperature and time. So the sensor uses this real-time thermal data, this temperature history, to accurately predict the concrete's current compressive strength in real time, continuously.
Whoa. So instead of waiting, say, 3 days, maybe 7 days for a lab result confirming the concrete is ready, The site manager gets a wireless notification, maybe to their phone or tablet, the very second that concrete hits the required strength, say 75% of its final design strength.
Precisely. That's it exactly. This is the definition of efficiency married to material integrity. Knowing the exact moment the concrete is structurally ready allows the site manager to speed up all the subsequent construction phases immediately and, crucially, safely.
Right, because they have the data to back it up.
Exactly. They can confidently tell the crews to strip the formwork earlier, which frees up that expensive equipment. Or they can mobilize the next trade, like the steel erectors, without any delay, knowing the foundation is solid. This not only guarantees the quality, because you have this continuous digital record of the material's strength development, but it also drastically reduces the costly idle time of cranes waiting, formwork rentals sitting there unused, and specialized crews just standing by. That downtime is incredibly expensive.
Okay, that synergy really paints the picture. BIM mapping the future, drones verifying the present conditions, and these embedded sensors confirming the material integrity in real time. That sounds like the operational model of smart construction. So let's move now from the tools themselves to the results, the tangible, quantifiable results, because this is where the source material really provides the hard evidence, right? How much time and money are actually being saved.
Yes, we have to move beyond just the theory. The promise of smart construction, when you boil it down, is simple. Fewer mistakes, faster timelines, and ultimately lower costs.
And the sources gave us a really powerful, specific case study detail, a recent project in Texas. It leveraged that daily drone surveying we just talked about, using it to monitor progress and verify quantities constantly.
Yes, that Texas project is often cited as a headline example of immediate ROI, return on investment. By really institutionalizing daily drone surveying, making it a standard operating procedure, creating that reliable, repeatable data loop between the physical site and the digital BIM model, the project team drastically streamlined their whole compliance and verification process.
And the outcome cited was stunning. A 40% reduction in inspection time. 40%. I mean, that's not just a marginal gain like saving a few hours here and there. That sounds like a fundamental overhaul of one of the most critical, often labor-intensive tasks on any construction site.
It really is, and it forces us to ask, okay, what does a 40% saving in inspection time actually translate to on the project's bottom line? Because it's not simply about an inspector getting, half a day back in their schedule. Inspection is very often what's called a critical path item in the project schedule, meaning the rest of the project, or significant parts of it, often cannot proceed until that verification step is complete and signed off. So shaving almost half the time off that critical process directly accelerates the entire subsequent sequence of work. Everything that follows can start sooner.
Okay, but let's be critical for a moment. Achieving that 40% reduction, it requires a significant investment upfront, surely. We're talking about buying commercial-grade drone fleets, licensing that sophisticated photogrammetry software you mentioned, probably retraining personnel. What do the sources say about that initial capital expenditure? Does that high upfront cost significantly eat into that impressive 40% time saving? Or is the ROI quick?
That's the essential business question, isn't it? And the sources did address this, usually through what they call life cycle cost analysis. They acknowledge that, yes, the initial outlay for the hardware, the drones, the sensors, the software licenses, and the training, it is indeed high. We could be talking 6 figures easily for a large construction firm to fully equip itself. However, the consistent finding was that the return on that investment, the ROI, is achieved remarkably rapidly. Sometimes within the first major project where these technologies are fully deployed, or even within the first fiscal quarter of deployment for ongoing operations.
That quickly. How?
Well, the ROI isn't just measured by calculating the reduced salary hours of the inspection teams, although that's part of it. More critically, the sources pointed again and again to the massive reduction in rework.
Rework, meaning fixing mistakes.
Exactly. Fixing mistakes made earlier in the process. Traditional methods, relying on less frequent or less accurate measurements, often result in disputes later on. Disputes over property line encroachments, incorrect elevations, inaccurate quantities of materials installed. And resolving these disputes often requires expensive demolition and reconstruction much later in the project, which is incredibly disruptive and costly. By catching potential errors almost daily, using that drone verification against the BIM model, you essentially eliminate the cause of many of these costly change orders and delays before they even happen. So the relatively small operational cost of running daily drone flights is minuscule compared to the potential multi-million-dollar expense of, say, tearing out and repouring a foundation slab that was poured slightly out of place or at the wrong elevation.
Ah, okay. So the primary financial benefit isn't just doing things faster, it's actually doing them right the first time, much more consistently. That cascading effect through the rest of the project must be enormous.
Absolutely enormous. And think about the supply chain acceleration, too. If the structural steel erection team is scheduled to arrive, but they're waiting for final verification that the concrete foundations are perfect, a 40% faster verification process means they can mobilize sooner. They arrive, the site is ready, they get to work. This allows the project to avoid incredibly expensive idling fees for specialized equipment, like those massive tower cranes, which can cost thousands, even tens of thousands of dollars per day just sitting there unused.
Wow.
And then there are softer benefits too. The ability to guarantee a project schedule completion date with much higher confidence opens the door to potential performance bonuses from the client. It also reduces overall financing costs for the developer, as construction loans don't accrue interest over unnecessarily extended timelines.
Okay, so when we synthesize all these benefits, the picture becomes really clear. Smart construction seems to turn these traditionally sequential, often stop-and-start construction tasks into a much more continuous, integrated, data-driven workflow. It saves time, it saves money, and it reduces both financial risk and structural risk, all at the same time.
That's a very good summary of the core value proposition, yes.
We focus quite heavily on the metrics, the time, the money, the efficiency. But construction is fundamentally a human endeavor, isn't it? Let's shift our focus now to the people involved, the human impacts. Construction is known for being inherently dangerous work. How does this big technological shift actively affect the people on the ground, in terms of their safety and maybe their sense of empowerment in their jobs?
This is a really crucial aspect, and frankly, it's perhaps the most compelling argument both ethically and practically for adopting these technologies. This transition is fundamentally changing the risk profile of the entire industry. When technology, whether it's a drone or a robot or a sensor, takes over tasks that are inherently risky for humans to perform, well, the safety benefits are immediate and they are dramatic.
The sources we looked at detailed some specific examples of how particularly hazardous environments are being managed differently now. Things like using autonomous tools to handle work at extreme heights, or in tight confined spaces where air quality might be an issue.
Exactly. Think about the leading causes of serious injury and fatality in construction globally. Falls from height are usually number one. Exposure to hazardous environments like trenches collapsing or air quality issues in confined spaces is right up there too. So, when a drone can fly up and inspect a deteriorating bridge or a high-rise facade, meaning a human doesn't have to go up on scaffolding or a lift, or when a small autonomous ground vehicle, like a little rover equipped with air quality sensors, can enter a deep excavation trench or a newly sealed storage tank before a human has to, you are completely eliminating human exposure to those high-risk environments. Full stop.
That's a powerful shift.
It is. And furthermore, think about highly automated tasks like using robotics for precise material placement or advanced machinery for heavy lifting and maneuvering. This reduces the physical strain, the repetitive motion injuries, for the workers who would otherwise have to perform that heavy, awkward manual labor day in and day out. So overall, this represents a really dramatic drop in the probability of accidents, injuries, and tragically, fatalities. It's transforming construction into a significantly safer trade to work in. It really is the definition of a win-win scenario where your operational efficiency goes up and human well-being is maximized at the same time.
That undeniable reduction in physical risk is huge. Can't argue with that. But the technology conversation, especially around automation, it always comes back to that common anxiety, doesn't it? The fear that automation will just displace workers wholesale, robots taking jobs. We probably need to address that fear directly. Based on the source material, does smart construction mean fewer jobs overall in the industry?
Yeah, it's a recurring concern, and it's understandable. But the source material offers a really critical counter-perspective here. The consistent argument is that this technology doesn't eliminate the necessity of human workers on a construction project. Rather, it elevates the role of the worker.
Elevates how?
Well, the repetitive, dangerous, or purely manual task might get automated, yes. But the need for human expertise in making decisions, in strategic oversight, in problem solving that need is actually amplified. We're seeing a distinct shift from primarily hands-on physical labor to more minds-on management and technical oversight.
Okay, so the argument is that people like site managers, project engineers, maybe even skilled trade supervisors, they're being freed up from the time-consuming, often tedious manual tasks like, walking a huge site for hours with a measuring wheel or manually checking inventories. And now they can actually focus on the higher-level complexities of the build, using the data.
Exactly. They are genuinely empowered because they are making smarter, better, and faster decisions based on this continuous stream of verifiable, high-quality data from the BIM, the drones, the sensors. They're moving away from constantly reacting to problems that are discovered too late, towards proactively mitigating risks that are identified early in the digital model, perhaps flagged by the daily drone feedback comparing reality to the plan. The key skills required to succeed on a modern construction site are fundamentally changing and arguably becoming more valuable.
That makes sense. So it probably necessitates detailing what those crucial skills are. Again, the ones that remain essential even with all these automated tools. If the machine is doing more of the measuring, the monitoring, maybe even some of the lifting, what specific functions are still uniquely and irreplaceably human?
Right. Our sources consistently pointed to 3 distinct high-value human roles, or maybe skill sets, that remain absolutely critical regardless of the level of automation deployed. First, and perhaps most importantly, is the skill of interpreting the data.
Making sense of it all.
Precisely. A drone can generate a gigabyte-sized point cloud file. A network of concrete sensors can report thousands of temperature readings every hour. But it takes a human engineer or manager to synthesize all that information, to understand the implications of that data. They need the domain expertise to spot the subtle deviations from the plan that might signal a future structural issue, even if it looks minor now. They need to translate the raw data, like maybe a clash-detected alert from the BIM model, into clear, actionable, site-specific instructions for the construction teams on the ground. This requires deep engineering knowledge and critical thinking.
Okay, so data interpretation and synthesis is number one. What's next?
Second, planning schedules and managing logistics remains a fundamentally human task, even with sophisticated tools. Yes, 4D BIM can provide incredibly detailed simulated timelines and identify potential bottlenecks, but the real world constantly throws curveballs, doesn't it? Unexpected extreme weather events, sudden geopolitical disruptions hitting supply chains for materials coming from overseas, subcontractor delays, even simple human error on site.
Yeah, reality is messy.
It is. So integrating that real-time data from the site back into these complex project timelines, managing the intricate flow of materials arriving from global sources just in time, coordinating the work of dozens of different subcontractors with competing priorities, that requires strategic oversight, constant adaptability, and the uniquely human ability to solve a complex, multivariable puzzle that changes literally every single day. No algorithm handles that perfectly yet.
Okay, interpreting data, planning, and logistics.
Yeah.
What's the third critical human role?
And third, and arguably the most fundamentally irreplaceable, is managing and leading the teams, the people aspect. Leadership qualities, effective communication, motivating diverse crews, resolving conflicts between different trades or subcontractors, establishing and enforcing a strong safety culture on site. These interpersonal, cultural, and leadership skills are entirely irreplaceable by algorithms or automated systems. No software program can genuinely inspire a crew that's facing a stressful deadline crunch. No robot can effectively negotiate a workable solution between 2 warring subcontractors. No AI can foster the kind of trust and collaboration needed to successfully deliver a massive, complex, years-long construction project.
Right, that human element remains central.
Absolutely central.
So the picture emerging here is that the job site is evolving significantly. And we should frame this not really as job elimination across the board, but more as a career elevation. The skills are changing. It sounds like the next generation of construction professionals are moving into roles that demand more strategic oversight, data analysis skills, technical integration knowledge, and strong leadership abilities. Moving, perhaps, from pure physical exhaustion to more intellectual engagement with the work.
That's a very accurate way to put it. The nature of the work is changing, requiring new skills, but potentially making the careers more sustainable and rewarding in the long run.
Okay, so we've established the digital foundation with BIM, drones, sensors. We've analyzed the pretty compelling efficiency gains and the ROI, and we've discussed the crucial human impact, both in terms of safety and the evolution of job roles. Now let's look ahead. Because innovation in this sector seems to be accelerating rapidly, we need to talk about what the sources suggest is the next big thing, or maybe the next wave, in smart construction.
Yes, the current wave of digitalization we've been discussing, the BIM, the drones, the sensors, you can almost think of it as the necessary prerequisite, the foundation, for the next potentially even more disruptive phase. And this phase involves much deeper levels of automation, driven specifically by artificial intelligence, AI, and also large-scale additive manufacturing, which most people know as 3D printing.
Okay, let's start with AI. We often think of AI perhaps controlling robots on the construction site itself, but the sources seem to indicate that AI-driven design is going to fundamentally change the very beginning of the process, the pre-construction phase.
That's right. This is where we get into the realm of computational architecture and specifically a technique known as generative design.
Generative design, how does that work?
Well, instead of a human architect or engineer manually creating maybe one, two, or perhaps a few potential design blueprints for a building,
Wow.
an AI algorithm takes all the project constraints you feed it, things like local building codes, the seismic requirements for the area, the desired energy efficiency targets, the client's budget limitations, the available materials, the specific geometry of the building site, and it rapidly generates literally thousands, sometimes tens of thousands of mathematically optimized design options that all meet those constraints.
Thousands of options generated by the AI.
Yes. The human role then shifts. It's less about manually creating the initial design from scratch and more about defining the goals and constraints very precisely at the beginning, and then curating and selecting the optimal solution from the vast catalog of options the AI presents, maybe based on aesthetics or constructability or specific client preferences. But the key is that this process ensures the structure is perfectly optimized for things like material usage, structural performance, energy efficiency before any construction even begins. It can further eliminate the kind of waste and potential clash points that even the most meticulous human planning team might sometimes miss in a highly complex design.
Okay, that sounds like it could compress the conceptual design phase dramatically, moving planning maybe from weeks or months down to hours or days for initial options. But the real star, I think, of future construction tech, the one that physically demonstrates this incredible speed, seems to be 3D printed structures. This feels like the technology that most dramatically changes the public perception of what construction even is.
It really is the pinnacle of current automation in terms of physical building. We are talking about massive, often gantry-style 3D printers, like huge robotic arms or frames that move over the building site. They operate largely autonomously, extruding successive layers of specialized, fast-setting cementitious materials, or sometimes polymer mixes, to build up the walls and structural elements of a building directly on the prepared foundation, layer by layer. And the staggering detail that came through in our source material, the headline number, is that entire houses, meaning the main structural shell, the walls are already being built in some cases in just 24 hours.
24 hours.
Yeah.
From foundation to roof-ready shell.
Yeah.
That number just absolutely redefines the concept of speed in this industry, doesn't it? I mean, a traditional stick-built house takes months. A custom home, maybe years, depending on complexity, labor availability, weather delays, material curing times.
Yeah.
How is that 24-hour speed even physically possible?
Yeah, it seems almost science fiction, but the speed comes from a combination of three main factors: logistical shifts and material science advancements. First, as you can imagine, there is virtually zero direct human assembly labor required for creating the main structure itself. The machine does the entire extrusion job, guided by the digital model. That removes a huge variable. Second, these printers don't use standard concrete or mortar. They use specialized high-flow cementitious mixes that have been specifically engineered in labs to cure extremely rapidly. They gain structural strength almost immediately after being extruded. This completely bypasses the long waiting periods associated with traditional concrete, needing days or weeks to cure before you can put load on it or build the next layer.
So advanced material science is key.
Absolutely critical. And third, the site logistics are radically simplified. The automated printing system primarily just needs a continuous supply of the raw material mix pumped to the nozzle and electrical power. This dramatically reduces the complex coordination needed for multiple different construction trades, the framers, the masons, the concrete crews who would otherwise need to come in sequentially, each doing their part of the structure. This shift really confirms the momentum we're seeing. The future of construction isn't some distant dream. It's actively being printed right now in various projects around the world.
Okay, let's quickly analyze the triple benefit of this 3D printing technology then, because it seems transformative beyond just the initial wow factor of that incredible speed.
Right. The sources highlight three main advantages driving its adoption. First, obviously, is the fast execution, demonstrated by that 24-hour build timeline for a basic shell. This potential for radical project acceleration means developers could theoretically scale up construction volume exponentially. This could fundamentally change the supply-side economics of the housing market, for example.
Makes sense. Speed is number one. What else?
Second, there are potentially profound sustainable methods involved. 3D printing can be inherently less wasteful than conventional subtractive construction methods. Think about it. The printer nozzle deposits the exact amount of material needed, precisely where it's required by the digital plan. This results in minimal site waste compared to processes that involve cutting lumber or blocks and disposing of all the offcuts. It also opens up possibilities for easily integrating recycled materials or industrial byproducts directly into the specialized cementitious printing mix, potentially lowering the overall environmental footprint.
Okay, speed, sustainability.
Yeah.
What's the third benefit?
And third, the potential for highly cost-effective outcomes. By minimizing the direct human labor input needed for building the main structural shell, by optimizing material usage through that generative design process we talked about earlier, and by dramatically accelerating the overall construction timeline, the cost per square foot or square meter of the basic structure can drop significantly compared to traditional methods, especially in high labor cost regions. This improved affordability could make housing more accessible and potentially lower the financial barrier to entry for large-scale development projects, both commercial and residential.
The momentum here seems undeniable then. Smart construction isn't just a minor efficiency upgrade for an old industry. It sounds like a fundamental redefinition of how we actually build our world, leveraging drones, sensors, AI-driven design, and now even houses that get printed faster than most of us can assemble a piece of IKEA furniture.
That's a pretty accurate, if slightly terrifying, analogy.
Okay, I think we've completed our deep dive now. We've really tried to extract the most crucial, high-value insights from all the source material we had on smart construction.
Yeah, and just to quickly recap the most impactful takeaways for everyone listening. We defined smart construction right at the start as that essential marriage of traditional engineering rigor with these advanced digital tools. We detailed the mechanics behind B.I.M. as that central intelligent database, the critical role of drones using photogrammetry for rapid site verification, and the huge time-saving power of those embedded concrete sensors using the maturity method.
Right, and we saw that concrete proof of its efficiency potential in that Texas project example, that headline figure, a massive 40% saving in inspection time. And we understood that translates into immediate ROI primarily by reducing costly rework and accelerating the entire project supply chain, not just saving inspectors time.
And crucially, I think, we moved beyond that common fear of job displacement. We saw how the sources argue this technology actually empowers the workforce. It shifts their focus away from dangerous or repetitive manual labor towards more critical roles in data interpretation, strategic planning, logistical management, and essential team leadership skills that remain uniquely human.
Exactly. And finally, we looked ahead to the revolution that's really already underway, highlighted most dramatically by 3D printed structures. The capability to erect entire house shells in just 24 hours, capitalizing on that trifecta of speed, sustainability, and potential cost savings, driven by specialized materials and those generative design principles.
And this incredible shift in speed and cost, particularly with 3D printing, it's so radical. It really forces us to consider the broader societal implications. It stops being just an internal industry efficiency metric and starts becoming a potential global game changer.
Exactly. And that is the final thought we really want to leave you with today. Something that builds directly on the power and potential of this new technology we've explored. If housing structures can be reliably built in just 24 hours, at a fraction of the traditional cost, and with minimized waste and potentially lower risk, what does this radical scalable efficiency really mean for addressing the critical global housing shortages that so many countries and cities face? And perhaps even more profoundly, thinking about resilience. What could this radical speed mean for the immediate rebuilding of vast urban areas after major natural disasters, earthquakes, hurricanes, floods? Could it fundamentally change the timeline and cost of humanitarian recovery efforts?
It's a powerful lens, isn't it?
Yeah.
A powerful lens through which to view the future of our built environment. Thank you for joining us for this deep dive into the rapidly evolving world of smart construction.
We'll see you next time on The Deep Dive.